Every single winter in the US, at least 1 septillion ice crystals descend upon the land. To wrap your head around that, just imagine a number starting with 1 and followed by 24 zeros. It's a scale that, well, it honestly defies intuition. Now, consider the paradox. Each of these crystals is a masterpiece of hexagonal symmetry, yet no two snowflakes share the exact same structure. How is it possible that 10 to the 18th power of molecules, behaving as a single unit, create designs where not a single one is a duplicate? The secret, it turns out, lies in the journey. No two crystals traverse the exact same path through the atmosphere. The odds of finding two identical flakes are 1 in 1,000,000 trillion. 1 in 1,000,000 trillion. That is the same molecular blueprint, but an identical journey. Today, we're going to uncover the unseen molecular scaffolding that dictates the shape of every single flake. High above us, tucked inside freezing clouds, a strange architectural process begins. This happens at brutally low temperatures, where the air is saturated with invisible water vapor. But here's the thing. This vapor cannot simply organize itself. It requires a catalyst, a nucleus. This is the moment of nucleation. Picture a tiny floating speck of dust, a single microscopic particle drifting through the freezing void becomes the anchor. When water vapor freezes onto these dust particles, the first ice crystals are born. An extremely cold water droplet captures this dust, freezes instantly, and the molecular construction project begins. It's as if the sky is launching a billion miniature construction sites all at once. Long before the invention of the microscope, humans were captivated by these geometric patterns. Back in 135 BC, a scholar named Han Ying observed that snow flowers have 6 points. It took centuries for this simple observation to evolve into a formal scientific inquiry. By 1611, the astronomer Johannes Kepler began questioning why snowflakes always fall as flat structures with 6 corners. He was searching for the universal law of nature that enforced this rigid symmetry. I find it breathtaking that people have been staring at the frozen ground, puzzled by the same hexagonal geometry for over 2,000 years, and we are still peeling back the layers of the ice's secret blueprint. Let's zoom in, past the dust particle, deep into the molecular architecture. This is the heart of the operation. As water freezes, the molecules align themselves into a hexagon, which is why every snowflake possesses 6 sides. It's a rigid, microscopic mandate. If you examine the initial crystal, the symmetry is absolute. In technical terms, this is hexagonal ice, or ice IH. Its structure is governed by space group 194, specifically P63/MMC, with symmetry D6H and a Laue class symmetry of 6/MMM. But here is the part that truly sparks wonder. This ice is not packed tightly. It possesses a relatively open, low-density structure with a packing efficiency of approximately 1/3. To put that in perspective, a simple cubic structure has a packing efficiency of 1/2, and a face-centered cubic structure is 3/4. It's an airy, spacious arrangement. Imagine these crystals as mirror images of corrugated oxygen sheets stacked atop one another. The fundamental structure is a hexameric box, where the planes consist of chair-form hexamers in the horizontal planes and boat-form hexamers in the vertical planes. At the center of it all, the unit cell of hexagonal ice consists of a group of 4 molecules. Just 4 molecules. These are the fundamental building blocks, the tiny, invisible handshakes that establish the 6-sided symmetry of every single flake. If we shrink down further to the scale of a single atom, the architecture becomes even more intricate. In hexagonal ice, water molecules employ a staggered hydrogen bonding pattern with 3 of their neighbors within the plane of the chair-form hexamers. It's a precise, interlocking puzzle. However, the 4th neighbor has an eclipsed arrangement of hydrogen bonding, creating a different kind of connection that binds the layers together. To grasp the scale, we have to look at the measurements. At 250 Kelvin, the hexagonal crystal has unit cell dimensions of 4.5181 angstroms and 7.3560 angstroms in the C direction. These distances are so infinitesimal that the average nearest oxygen-to-oxygen distance is just 2.76 angstroms. Even the bonds themselves are microscopic. The hydrogen-to-oxygen and oxygen-to-hydrogen bond distances are 1.75 angstroms and 1.01 angstroms, respectively. There's a peculiar detail here. The unit cell of hexagonal ice is 0.3% shorter in the C direction. This tiny discrepancy causes reduced compressibility in that specific direction. It's as if the crystal is being slightly squeezed, granting it a structural integrity that dictates exactly how the growth will progress. Now, consider the descent as a chaotic, swirling odyssey. Snowflakes do not simply drop in a straight line. Instead, they swish, swirl, and corkscrew through the air, tossed by shifting winds. This is where the science transforms into art. Every single crystal acts as a physical recording of its own unique history. Because the atmospheric conditions, temperature, and humidity shift constantly during the fall, the shape, size, and pattern of a flake are a direct result of its specific path to the ground. 2 crystals that begin in the same cloud but drift through different air currents will emerge as entirely different designs. The molecular scaffolding we discussed earlier is carved by the environment. The sky uses the atmosphere as a chisel, and the journey itself becomes the artist. Now let's address the color. If you look closely at a single snowflake, you'll realize it doesn't actually have one. Snowflakes are colorless. So why does a winter storm leave a blinding white blanket across the landscape? It's a matter of pure physics. Snowflakes appear white because they are translucent. Light doesn't simply slide through them, it's scattered and reflected in 1,000 different directions. When you see a white field, you aren't seeing a pigment, but the result of light bouncing off countless tiny translucent crystals. There's something poetic about a clear, colorless crystal wrapping the entire world in white. Beyond the clouds, the physics of ice reveals even more variety. In nature, there are 4 primary morphological forms of hexagonal ice: snow, firn, which is multi-year snow, freshwater ice, and sea ice. Each is a different expression of the same molecular law. Yet, if we move into a laboratory, we find a strange anomaly: cubic ice. Unlike the hexagonal variety, cubic ice contains solely chair-form hexamers. It's a structural departure, using the same water molecule and the same temperatures, but a different geometry. This proves that while the blueprint is universal, the environment is the true sculptor. While we often think of snow as a uniform blanket, there are outliers that defy expectation. In the grip of a brutal winter, you might encounter something incredibly rare: diamond dust. These are tiny, shimmering shards of ice, some as thin as a human hair. It's a staggering contrast in scale. On one end, we have these microscopic needles. On the other, we have giants. The largest snowflake ever recorded was 15 inches long. Imagine a single crystal structure the size of a dinner plate, dwarfing every other flake falling from the sky. But there is a deeper, stranger layer still. Even the rigid hexagonal structure isn't as stable as it seems. In reality, hydrogen bonding in hexagonal ice is somewhat random because protons can move between water molecules at temperatures above 5 Kelvin. It's a chaotic dance on a scale we can barely conceive. Protons in ice likely behave like a quantum liquid in a constant tunneling flux, shifting and sliding in ways that defy classical physics. Neutron scattering experiments have confirmed this, showing a proton scattering density midway between oxygen atoms. This reveals a state of proton delocalization. It means that at the very heart of every snowflake, there is a quantum mystery still humming away. From a single speck of dust to a dinner plate-sized giant, the snowflake is a masterpiece of conflicting forces. It's governed by the rigid mathematical law of the hexagon, a blueprint shared by a septillion crystals, and yet it's shaped by the chaotic, unpredictable currents of the atmosphere. With 10 to the 18th power of molecules coordinating their every move, the odds of two flakes being identical remain 1 in a million trillion. Each snowflake is not merely a piece of frozen water, it's a physical map, a frozen recording of a journey through the sky that can never be repeated. We're left with a haunting realization. While the molecular laws are universal, the experience of every single crystal is unique. If the proton dance at the heart of the ice continues to defy our physics, what other secrets are hiding in the simple act of a snowflake falling?